Hello, everybody, and welcome to Mr. Saucedo's YouTube videos. Today, we're going to be talking a little bit more about the continents, but specifically continental drift. So to start with, the last thing that we talked about were plate boundaries. And so I mentioned the fact that along a lot of convergent plate boundaries, and even divergent plate boundaries, we get a lot of volcanoes. So what exactly is a volcano? A volcano is an opening in the crust that exposes the upper part of the mantle to the atmosphere. And so when we think of volcanoes, okay, or Camerupt, right? But when we think of volcanoes, most of the time we think of them as being extremely far away and gigantic. But in reality, we do have volcanoes in California and in Oregon. They're just, north of us. They're in Northern California. But most volcanoes are created by the subduction of plates or the spreading of those plates. So we're talking about convergent and divergent plate boundaries. And so the earliest life that we can possibly find probably lived off of these chemicals. So they lived off of, chemicals from underwater volcanoes that were releasing CO2 and hydrogen sulfide, basically venting it into the ocean. And so there actually are organisms that still live and survive off of this, and they utilize this mechanism. So we have hydrogen sulfide, we have carbon dioxide, and they can utilize that in order to make sugar with water as a byproduct and also sulfur as a byproduct. And so this is a very specific type of chemosynthesis. So we have photosynthesis, we have cellular respiration, and we have chemosynthesis, which, again, bacteria still use to this day in these underwater vents. And as far as we can tell, that's probably how most life on Earth started, right? From these underwater vents and the ability for these bacteria to be able to manufacture sugar. So continental drift, what exactly is that? Well, all of the plates that we've been talking about for the last couple of days are involved, and the continents move about the rate of an inch or more every single year. So if we wind it back 200 million years ago, all of the continents were together in a giant landmass that we call Pangaea. And so here's an animation of the breakup of Pangaea to where our continents are now located. And you can see basically that there basically is a huge movement of, in particular at the top, they start to separate and go outwards. And then towards the middle, same exact thing. You can see Africa and South America very clearly separating from one another. And so the land masses on Earth have also, though, changed shape. So they don't perfectly fit together into what we would consider Pangaea today, right? We can't just piece everything back together and get a perfect Pangaea because, ocean levels rising and falling, plate tectonics, pieces of the continent maybe breaking off, all of that, or weathering, erosion. That's going to cause some differences. But it's a pretty cool thing that we've been able to piece back Pangaea, and we can go back even further than that to see what things were like pre-Pangaea. So continental drift is a huge idea, especially since we're going to be focusing on evolution and natural selection. So what are the kind of proofs of continental drift? Well, one of the big ones is going to be the fact that animal and plant fossils are found on opposite continents in previously joined continental areas. So for example, if we take a look here, you can see we have fossils in different colors that are found in different places. And obviously, South America and Africa are now no longer near each other at all, but we find these fossils in both places. Same thing with Antarctica and India and Australia. We find common fossils between these areas, even though they're not currently together. That probably means that they were joined at some point. Glacial deposits have left scratches on rock, and they are very consistent with Pangaea. So obviously Antarctica is still basically a giant glacier deposit anywhere, right? It's just frozen. But the bottom of Africa isn't, the bottom of South America, the bottom of India, and the bottom of Australia. Okay, not a lot of snow in a lot of those places. So the fact that we have these scratches in a direction, that kind of leads us to believe that they were probably joined together at some point and that the movement of the ice was in a particular direction. It just took a really, really long time. We also found seashells and marine fossils near convergent boundaries, which makes sense because remember, we are literally pushing things up. And so if you're pushing things up, that means that the lower layers where the older rock is going to get pushed closer towards the top as they converge together. And so here we go. Here are some seashells and some sedimentary rock layers. Good old shelter. And the other thing is that we have found the age of rocks in divergent boundaries. And so what we have found is that the closer you get to the divergent boundary, well, actually, I should probably just read this directly. It'll probably make more sense. So the newest rock is near the actual boundary line, and I'll show you that in a picture in a second. So right here, you can see that the newest rock, that's going to be the redder color, and the oldest rock is going to be further from it. So you can see that the oldest rock is right here along the east coast of the United States and along the east coast of the United States and along Western Africa. And then as we get closer to that Atlantic ridge or mid-Atlantic ridge, that's where the new rock is being generated. And so those rocks are a lot newer.